Hello and welcome to this GCSE Physics revision video looking at energy resources. I want to show you where our energy comes from, how we use it and evaluate some of the many advantages and disadvantages of various energy resources. It forms the basis of many 6-mark exam questions, so you'll really benefit from knowing it all. So if you've got the energy, let's go. Taking an image from one of the earlier videos in this energy series, we can see that there are 9 energy stores and 4 energy transfer pathways. We're going to look at which ones we use most often in our homes, offices and schools. Focusing on the transfer pathways first, how do we use most of the energy in our home or office? Or rather, what I mean is, which transfer pathways do we use? We use each of the 4 transfer pathways in one way or another on a fairly regular basis. We transfer energy by heating whenever we cook our food or heat our homes. We transfer energy by radiation as we use any lights or listen to music. We transfer energy by electrical work whenever we use any of our modern electrical devices. And we transfer energy by mechanical work each time we use a force to make anything move. We tend to use the electrical and heating pathways most often, so I want to just focus on these for a second or two. Taking heating first then, it's important to remember that it is an energy transfer pathway, and so it will have an input store and an output store. The input store will often be something like the chemical store, for example in the form of fossil fuels like coal, oils or natural gas. We should include the chemicals in our food here as we heat our bodies during respiration. A geothermal input uses the naturally high temperatures under the Earth's crust to heat water for some homes. The output stores are the thermal stores in heated items, whether they be foods, rooms, water or whatever. So heating is a really convenient pathway when transferring energy to the thermal store. Fossil fuels are often used as an input, but this is becoming less so as we move towards more renewable input sources, as we'll see later. Electrical work is another transfer pathway that we often use, particularly at home. It's a really convenient pathway for transferring energy to the home for a wide variety of uses. Most electricity is produced in a power station and is delivered to our homes via the national grid. Different types of power station use different stores as their input. For example, electricity companies might use chemical stores, nuclear stores, kinetic, gravitational or geothermal stores as their inputs. We'll explore each one of these in more detail later and discuss the benefits and drawbacks of each one. The output stores from electrical work as we run our devices are also varied. Thermal stores increase as we use electrical heaters, kettles or electric blankets to keep us toasty and warm in bed. Kinetic stores increase as we drive our electric cars or use the elevators in office blocks, hospitals or shops. And vibrational stores increase whenever we use our phones, music players, games consoles or computers. Our mains electricity comes from a power station, and there are different types. Try pausing the video here and see if you can match the energy store on the left, used by each type of power station on the right. Not all stores are used, and some may be duplicated. Power stations that burn fossil fuels will use a chemical energy store as its input, as will those burning biofuels like wood or paper. Nuclear power stations obviously use the nuclear energy store as the energy is released from fission or even fusion reactions. Wind, tidal or wave-based power supplies use the kinetic stores from the movement of air or water. A solar array uses the nuclear store inside the sun as fusion reactions take place between hydrogen nuclei. The energy is radiated to us through space and collected in solar panels. Hydroelectric power stations use the gravitational store as water flows downhill to rotate a turbine. And geothermal power stations use the thermal store beneath the Earth's crust as cold water is heated by the Earth's high temperature inner regions to make steam which passes over a turbine. Most electrical power stations use a turbine and a generator to convert rotational motion into a flow of electrical charge. If we rotate a coil of wire inside a magnetic field, we induce a potential difference across the wire. This leads to a current, or a flow of charge, in the wire, which could be measured by an ammeter. So all we actually need is some way to rotate the coil of wire. Inside many power stations is a turbine, which looks like a giant fan. You can see in this diagram that water is heated in some way and turns to steam. The steam blows over a turbine and causes it to rotate. The turbine is connected to a coil of wire inside the generator. The induced current is then fed via large wires to the national grid. This is a huge network of overhead electrical cables which some bright spark invented to carry the electrical current to all of our homes and offices across the country. The main differences between different power stations come from either the fuel used to boil the water to produce the steam, or from the different methods to rotate the turbine. This simplified diagram shows that electricity is produced from a rotating coil inside a magnetic field. A turbine is used to rotate the coil. High pressure steam causes the turbine to rotate in the same way that a child's toy windmill rotates as they blow on it. Water is boiled in a number of different ways to produce the steam. For example, one method would be to burn fossil fuels such as gas, oil or coal. Or a nuclear reactor may be used to create the high temperatures needed. Some burn biofuels such as wood, or others use the naturally high temperatures deep inside the Earth's thin crust. Other power stations don't use steam but rotate the turbine in other ways. Wind, wave, tidal or hydroelectric stations, for example, use the flowing or moving water or air to rotate the turbine. Lastly, there's the solar power station, which uses the radiated energy from the sun to generate electrical currents in photovoltaic cells. So let's take a look at each of these methods in turn and explore the advantages and disadvantages. So taking the fossil fuels first, the advantages are that they're cheap to use. We simply dig them up out of the ground. They also have a high energy content, which means that a lot of thermal energy can be released compared to their mass. The disadvantages, however, include the huge quantity of carbon dioxide that is released into the environment. Atmospheric CO2 is known to be a greenhouse gas and is a major cause of global warming. Fossil fuels also contain other elements such as sulfur, which burns to produce sulfur dioxide, a major cause of acid rain which kills plants and destroys buildings. Another disadvantage is that fossil fuels are going to run out if we don't stop using them. They took millions of years to form from dead plants and animals, and we're using them at a colossal rate. Nuclear power stations rely on the nuclear fission of uranium to release large quantities of energy. If a uranium-235 nucleus is hit by a stray neutron, it becomes so unstable that it splits into two smaller nuclei. This splitting, or fission as it's called, is accompanied by the transfer of a huge quantity of energy to the thermal store. In other words, the temperature increases rapidly. At the same time, 3 other neutrons are emitted, which could go on to collide with 3 other uranium nuclei, and the process is repeated. The energy released can be used to heat water, to produce steam, to rotate a turbine, and the rest you know. The advantages of using nuclear energy are firstly that the process is very clean. There are no pollutants such as carbon dioxide, soot or acidic gases being pumped into the atmosphere. The other main advantage is the high energy density of uranium-235. A relatively small mass of uranium can heat a huge quantity of water. It's not all good news though. The waste products of nuclear fission are themselves radioactive and will be for a very long time, so need very careful disposal. We need to make absolutely sure that these products won't ever find their way into our water supplies or our food. Currently they're buried in deep underground concrete containers. For now they're safe, but in the future, who knows? There's also a very small but very real risk of explosion or radiation leak from the power plant itself. It's happened before in places like Chernobyl, and it could happen again. If it does, people in the immediate area could suffer very severe and very rapid health problems, or even death. Not only that, but the radioactive products could easily find their way into the local environment or spread far and wide in the air, on the wind, to neighbouring towns, cities, or even countries. Fortunately, nothing could possibly go wrong in this part of the country.
Spider-Man, Spider-Man, does whatever a spider can. Spins a web any size, catches thieves just like flies. Look out, here comes the Spider-Man.
Biofuels such as wood, ethanol or biogas are fuels which are specifically grown or produced for burning. They're advantageous because they're renewable. We can simply make more of them. New trees can be planted and grown. Microbes such as yeasts can ferment more sugars into ethanol. Or bacteria can decompose more waste matter into biogases such as methane. Their production is largely under our control. While biofuels do release carbon dioxide when they burn, it's only the same quantity of CO2 that they took in from the atmosphere during their production, so they are in fact carbon neutral. The main problem with biofuels is their low energy density, so large volumes are required in order to release the quantities of energy needed for electricity production. Geothermal power stations use the Earth's natural thermal energy by pumping cold water deep underground, where it's heated into steam to be passed over the turbine. The overwhelming advantage here is that the high temperatures within the Earth are continuous and so are renewable. The potential problems come from drilling deep into the crust. This can cause the release of previously trapped natural fossil fuel gases into the atmosphere, and it can also destabilise the land, leading to collapses or even earthquakes. Next we have the wind and water methods. Wind turbines, which people often wrongly call windmills, can be built on exposed areas of land or out at sea where strong winds will blow over the turbine blades directly. They automatically change direction to face the prevailing wind direction in order to maximise their rotation rate. Waves at sea can also be used to push air over a turbine. As the sea levels rise and fall with each wave, the air above is pushed into a specially built and sealed chamber. Sea tides rise and fall twice each day as the Earth and the Moon rotate around each other. With each tide, seawater will flow towards or away from the shoreline. Turbines can be built beneath the surface of the sea and made to rotate as water flows in both directions. Hydroelectric systems use water that has been made to build up in huge reservoirs behind man-made dams. When needed, the dam can be opened and the water allowed to flow over the turbines. So taking the wind and water systems together, the advantages of all these systems are that they are clean, with no polluting gases and totally renewable. As long as our planet remains as it is, and in our current position in the solar system, we will always have wind, waves, tides and rainfall. And don't forget, producing electricity from wind is easy. In fact, it's an absolute breeze. The problems, however, include the relatively low output, and the fact that the output is variable and fully dependent on the weather conditions, so it's not particularly predictable. Finally, the noise produced by wind turbines puts many people off from using them. It certainly limits where they can be built, away from residential areas at the very least. The last method of producing electricity uses energy radiated directly from the sun, as photovoltaic cells create an electrical current from the light which falls on the solar panels. This method is clean, renewable, silent, and the panels can be placed into existing sun-facing buildings. The energy output, however, is variable. It's weather dependent, and until the technology improves, huge solar panels are required in order to make a significant contribution to the electricity supply. So there you have it. We've seen where our everyday energy comes from and how we use it to generate our most convenient method of transferring energy, electricity. Hopefully you'll have seen for yourselves how the different resources can be used, how some are more polluting or harmful than others, or how some will continue to be renewable for many, many years to come. Please make sure you stay in touch for some great science content, new material or revision tips. If you have the energy or the resources, you can contact me via my website plutoniumscience.com or via my Twitter at PU94Science, or just email me directly. Keep up the good work and good luck with the exams. Take care.